Thank you, and everybody hear me, I guess. What I want to show you, I'm actually going to show you the programs. In trying to get the kids interested in astronomy or anything else, a lot of times what we'll do in teaching them coding, as I learned a few years ago, if I start out with straight Python, sometimes it's a little boring to them. And so what we're trying to do, there are several of us around the country who are putting in time with something called GlowScript or VPython. How many people have worked with VPython or GlowScript? Some people have. If you ever take a course called Matter and Interactions by Bruce Sherwood and Ruth Chabet, that's one of the cornerstones of there. So what they've done is they've developed some packages. And if I can get the right one up. So it looks like this. And what it is, it's a browser-based operating system. You're talking about JavaScript. I think it's all interpreted Python. If I remember correctly, it's written in JavaScript. But it is Pythonic. And these are up and coming. Some people may have used Replit in the past. But one thing, if I want to create what's called a trinket, look at all the languages that it will do. It'll do Python. It's very limited. It'll do a premium-based Python 3, which is what I will often prototype my code with because I can use Matplotlib and NumPy and all those. But it'll also do R. I haven't tried that because I'm not an R person. I haven't tried it with Java, but let me show you some of the GlowScript stuff. So how many people know what Friday is? I saw T-shirts. Well, a friend of mine who was down at, I think it's southeastern or southwestern Louisiana State, and you can see the name of the planet up there, Red Elaine, who advised Mythbusters and is advising MacGyver now, wrote a program in Python that simulates a 2-star planetary system. And so this is one of the assignments I give the kids. And this is what it looks like. Sometimes it takes a few seconds. And so not only is it's not just 2D, but it's 3D. And I can zoom in, zoom out, do all sorts of cool stuff. So that's one. And we often ask what happens, and sometimes Red Elaine wrote this in Wired Magazine. He also writes for them. What does it look like for the space shuttle in relationship to the Earth as it goes around? Everybody thinks it's so high, and I've forgotten, is it 400 kilometers up, something like that? 200, okay. So he wrote a program on this. This is not mine, but you can also add in such things as a picture of the Earth with the ISS going around it. And it gives them a little bit of perspective about how big our big blue planet is, how smooth it is, but how close we've actually been to the Earth's surface. So a couple of them also that I've given, and the kids are working through some of these now. There's a group called Pickup, Partnership for Integration of Computation into Undergraduate Physics. If you're not familiar with this organization, they have a huge amount of exercise sets in many languages at many levels. And here is one with the binary in spiral. And once again, the kids have to write the code. This comes with a full lesson with, and I'm not selling this, it's just, it's something that's very useful to me. When you run it, it gives you not only the in spiral, but also a graph that has a very interesting finish to it, which I think we all know. Unfortunately, I don't see the, at the end, I've got to rewrite this one because it doesn't show the very end part, but it's pretty darn good. All this, and my kids are programming it in high school right now. Now, I have an exceptional group of kids, but it can be done at many different levels. That look familiar to people? Okay, it certainly does to me. I might just have a T-shirt or two with that on it. Right now, as I'm speaking, my kids are doing this program. We're developing where they had to go and get information on where Mars is right now, as you can see in here. They got some information, and in this particular one, and they actually are doing this as we speak. If I click on this, or if I actually start it, that would be a help. But they have to know when to launch and when it's supposed to land and where it's supposed to go. Once again, I can change the perspective of it and do a lot of different things on it. And if you're curious about, this came out after The Martian, by the way. A friend of mine, Aaron Titus at High Point University, actually put this together. Once again, it's a whole set of activities. I'm not going to show you the lunar landing, but that is a cool one because it's a game. Once again, kids have to write it. It's all in Python. And the final thing, I did, in fact, put together a lesson. All these, by the way, are linked on the PowerPoint that I put into the page. But for example, how easy it is, if I write the word sphere, it creates a three-dimensional sphere. And this is a whole set of lessons that I usually start my classes off with. So, and you can do funky things with it too, change the color and put it in a different position. And a friend of mine, Byron Philauer, even did a projectile one where he had a basketball player shooting a basketball and you had to do calculations from it. You can input things, you can do an awful lot of things with it. So just wanted you to see what we're doing at my end. Hopefully some of my kids will come your way sooner or later. Thank you.
So, is this on? Okay. I was a part of Google Summer of Code 2017. So Tom Aldcroft, Martin Van Kerkwich, Hans Moritz Günther, and we tried to do a very ambitious project in AstroPy, which was seamless combination of SkyQuad, table, WCS, and FITS. So the first time I saw this project, I was pretty overwhelmed because it has so many terms that I had no clue about. So the idea was basically AstroPy came into being as a combination of ASCII table, PyFits, a lot of modules. But the point was to make it more cohesive and to make it, basically adding seamless interoperability between the different constituents of AstroPy. So what I did was I implemented the FITS time standard. Okay, since it's not here, I'll show you the. So the first thing was I had to solve this very famous hashtag 3000 issue. And that issue had been open for the past 3 years. And it had been open for the very reason that storing time coordinates in the FITS world coordinate system requires you to have a knowledge of the FITS time standard. It requires you to have a knowledge of the world coordinate system. It requires you to have a knowledge of astronomical time and the multiple scales that it has within it. The FITS WCS papers, 4 of them have been released. And at the same time, you need to know the time class. You need to know the FITS module. And to be honest, the FITS module hasn't been changed for the past 12 years. So that code, I still have nightmares when I see that code. So, so we decided to first work with time because time has a specific standard defined as opposed to SkyQuad and, as opposed to SkyQuad. So then, so time as a dimension in astronomical data presents a lot of challenges for it to be stored in the FITS standard. And the main reason is that it has a lot of metadata associated with it, right from the scale, the format, the location, the precision, and you don't need to know about delta, UT1, UTC. It's a concept about, I think most of you people must be knowing, but it was quite new to me that there are actually some leap seconds which are added to UTC time, which make the atomic time and the UT1 time to sort of coordinate with respect to each other. So, so mainly my work was to allow time coordinates to be stored in the FITS world coordinate system. And yeah, I would like to say that the first PR that I opened has 315 comments, which is the most commented PR in AstroPy. And it was for the same reason that I think I had to change the implementation about 20 times. I had to change different user the parameters and the arguments and the features that are provided. And every time someone would review, they would have new comments and new features to be added. So, yeah, at the end, I somehow got to the point where, okay, this can be merged. And after a lot of rebasing and a lot of merge conflicts, I was able to get this merged. And yeah, so uh, after that, I also not just storing time coordinates to the FITS world coordinate system, I was able to even add the feature where we can read time coordinates from arbitrary FITS files. And the problem here is that the FITS standard provides a lot of flexibility to the astronomical community, and at the same time, it is very intricate and it is quite beautiful. But then that just made my job more difficult. So I had to take into account different user perspectives and different features that can be provided. And so, yeah, now AstroPy has a full-fledged time fit standard. And so, yeah, that's just a background study that I had to do related to astronomical time, time standard, and the world coordinate system. And just one thing which I I just want you to read this. This was what I read the first time when I saw what is a second in the ERFA documentation, and that's it. I knew that I am up for a task. So, yeah. And my beloved mentors always used to say that this has been an issue for the past 3 years. Everyone says it's easy. We know it's not. So, I just have this conclusion that FITS is just much more, much more than just an image format. So, thank you.
Yeah, so I'll explain a little bit about the SunPy database package, which is a pretty unknown but a useful package which SunPy has. And so when you're dealing with lots of files, what tends to happen is you write a lot of code just to process those files and organize those files. You need to maintain a directory structure, and you just need to do IOs and maybe rename the files, keep them in specific folders. Just there's a lot of overhead just to organize your files. So what the database package enables you to do is just organize your files in a very efficient way, and and use them in a very efficient way. Also what this allows you to do is you can save your state of your files in a database like a SQL or a remote database, and you can share it with others also. And you can so if you're using the same Python session, you can save the state of the database persistently on the hard disk, and you can resume it as it was on a different Python session. Um, so some of the useful operations it supports is starring entries, tagging entries, and it also maintains a undo redo stack. And it also has a caching feature, which means that you do not need to re-download files which you already have. I'll just show them. I'll just show how each of them work. So basically, what the database module maintains is for each file, it uh, tends to create database entries, and the database entries broadly they just have these attributes. So, um, so So this is a sample of some of the entries in the database. So this is what the database will look like. This is an example database. So for each file header, you will have a database entry, and you will have parameters like the ID, the start time, end time, wavelengths, and the path for the file. So where it becomes useful is So suppose you have a directory of its files, you can just pass that you can just pass the name of the directory, and it'll make a database. It'll make an entire database. It'll make a database like this, consisting of data from all the fits files in the directory just from one statement. Also, you can just search for the date range you want and the instrument you want, and you can just directly download the files using the database module. So what you'll do is you just give the instrument name and whatever details you want. You'll automatically download the files, keep them in a directory, and populate the database according to that. So it just makes your life very easy. This has inbuilt caching, which means that so if you have two big queries which overlap with each other, so this ensures that all those files in the overlap area which you've already downloaded, you don't re-download them again. So you save a lot of bandwidth and just time. Also, if you have a big query downloaded and you want to make sub queries of that query, it makes sure that it will not download any of those files. So it makes sure that you just download only the new files which are not there in your system. Yeah. So another useful feature is tagging entries. So you have a lot of files, maybe you want to tag them. So in this example, what is shown is it's tagging the entries which are in the month of March, April, and May. It's tagging them with spring. So you can select a subset of entries and tag them so that you can retrieve them later as per your convenience. So like if you're using some files for project 1 and some files for project 2, you can just tag them with project 1, project 2, and get them later. It also maintains undo and redo stack, which is very, very useful. This undo redo stack is also, I think, it's stored persistently. So it's like a version control of how you're using your files. So if you like screw up 7 days from now, you can just roll back your file states. You can also query the database. It's very easy. So once you have all the files, once you have the database made, you can query the database and get the specific entries which you want. So like if you want a specific date range or some specific wavelength, you can just query the database and get those entries. So yeah. So it's a very useful module if you want to organize your files efficiently. That's it.
So I've been all fired up about Gaia, so I thought I would just show a quick example of how you could go from the name of a star to its orbit in the Milky Way using two packages that I've developed, one of which is an AstroPy affiliated package called Gala. So you can install them using that line at the top, pip install astro-gala, and then Pya, that's the other one. By the way, never do live demos, but I'm about to do a live demo. So, and which does a remote database query on the fly. Let's see what happens though. Okay, so the first thing we can do is, given the name of a star, we can use what's built into AstroPy already to get the sky coordinates of that source from Simbad. So let's see if that works. Okay, good. So now I can look at, you can see it pulls just the right ascension and declination for that target. Now I can use this object from Pya, this Gaia data thing, to do a query remotely to the Gaia archive to grab the Gaia data for this source. So we'll do that. Hope that works. Nice, it worked. So now I get back this Gaia data object with a row, which has attributes with all the Gaia data. So you can see it has a pretty large parallax, so it must be something that's pretty close. It's a pretty bright source, 7th magnitude star. So now I can, from that object, get out a sky coord object that has all of the phase space coordinates. So sky position, distance, it does 1 over the parallax to get distance, proper motions, and radial velocity, which is in the Gaia archive. I have to turn that into something called a phase space position, which is something that Gala knows what to do with. So I do that by transforming the full space coordinates to a galactocentric frame, get Cartesian coordinates out of that, get my Milky Way model here, integrate an orbit, and then boom, there it is. So that's the orbit of the star within the Milky Way, roughly. I mean, I didn't look at error bars or anything like that. You can also... Gala has an extensive test suite that is about over 90% covered, I believe. So yes. You can go to other representations. So that's Cartesian. Here's cylindrical. You can make quick plots like that. Compute other orbital properties. And then you can also take the orbit, which is now this thing in galactocentric coordinates, and go back to some astronomical frame, heliocentric frame, which in this case doesn't really make sense because the sun will have moved while I've integrated the orbit of this other thing. But we can pretend and plot where that star's orbit would be if the sun stayed fixed and look at where it was on the sky. So that's my 45-second demo of going from a star name to an orbit in the Milky Way.